So, I'm Björn. I'm a production engineer at SoundCloud, which is a company that puts sounds into the cloud. We also have, it's true, we have interesting use of MySQL, but that's not why I'm here. You can see why I'm here, there, and there. Like, I'm the Prometheus person in the company, and Prometheus was initially developed mainly at SoundCloud, which kind of ties me to that project. But if you're into MySQL and you want to work at SoundCloud, we are also hiring. Cool. So, life of a PromQL query. I was kind of teasing this a bit in the keynote. But I first have to put here my most favorite slide I ever made, which is about like time series in general. Time series databases seems to be like the hype topic at this conference, which I didn't expect. But yeah, nice. And people talk about like time series databases are heavy on write and light on reads. And then some other people say, no, it's the opposite. And my opinion is TLDR, the time series databases are special because they're vertical writes and horizontal reads. So what does that mean? Actually, I mean, the screen is so close, I can just point, right? I like to point. So, although now I'm on the wrong side. So, I put in this graph, I put time series on the y-axis, and then this is like the scale that you have at Prometheus, but that might be different in different use cases. So, Prometheus server has millions of time series. Now, I should have made like 1 million lines here, but the resolution of the projector is not quite sufficient to have 1 million lines here, so I just put a few here. These are time series, and you see the x-axis is the time dimension, which of course might be years or something. In the Prometheus case, we consider Prometheus more like a matrix cache, so it's more like a weeks thing. And then you see time series that just last all the time, which you might think is the normal case, but then we are there for the cloud-native environment. So we monitor pods on a Kubernetes cluster, for example, and they come and go. So you quite typically have this thing that the time series just stops because this pod ended its lifetime, and kind of the replacement pod was scheduled just before with the new software version. So that also happens all the time. And since in the Prometheus case we mark all the time series by all kind of labels, you get new time series for new pods because it has the pod IP number or the software version tagged on it. So that's a pretty typical scenario with time series. Now, vertical writes means in a short time frame, you will update every current active time series that hasn't ended yet, and that's those rectangles here, right? So you write a new data point to every single time series, not necessarily at the same time, but like in a short time frame, in one scrape cycle in the Prometheus case. Then you do it again, then you do it again. So they are all written to with tiny updates of just a single sample all the time in vertical fashion. Now, horizontal reads, that's what you do if you have a dashboard. Like you want to graph one line on your dashboard. So let's say it's the long-term dashboard for like the whole week or 2 weeks. So you grab one time series from your time series database and read all the data horizontal, right? Horizontally. Sometimes you graph more than one graph, of course, that's kind of symbolized by that one. And as we will see later, with like PromQL, you can also aggregate on the fly. So you might also draw just one graph that is aggregated from 2 time series, and then you get this one. This goes up to like, let's say, thousands of time series. That's becoming abusive in the Prometheus case if you want to aggregate 1,000 series. But it would still be a tiny space of this millions of time series space, right? So it's still kind of horizontal-ish. Now, there are other queries. I tried to put this here. So this is a query that just looks at the current state. It's very typical for an alerting rule. PromQL is also able to write alerts. And then you have something like, what's the current state of the world? Should I alert on it? And then you have an expression that just touches stuff in the immediate present. In theory, you could, of course, query it in the past, like, what was this instant value last week? Sure, that just doesn't happen so often. So that's typical for that. And that might actually also aggregate loads of time series. But then there's this square query, right? Square queries, whatever. So this happens quite sometime. There were loads of super awesome time series and metrics talk at this conference, and I remember people talked about counters, how you measure counters, and then if you take the first derivative of a counter, you get something like QPS. So this is why you need a bit of the past for something like that. If you want to alert on, I have so many QPS, or we had this in the keynote, like my QPS is now lower than I expected, you have to calculate the current QPS, and then you have to look a bit into the past, like 2 or 3 samples, couple of minutes, whatever, right? So it's still this kind of square thing at the beginning of the time scale, which leads me to the case where this is all in memory. If you manage to fit everything in memory, great. It's called random access memory for a reason. This whole vertical, horizontal thing doesn't really matter. You can just access everything all the time, right? Oops, that is... our security team requires me to make my computer lock if I talk for too long. So, but this is my favorite slide. So, where was I? Yeah. So this is in Prometheus. We have this weird requirement. We want to have a lot of metrics, like all the 2 weeks, on a single host with local storage. So we don't want to depend on a distributed storage. That's probably down when you actually need your monitoring system most dearly. And then, so that means we have more data than fits into memory. And then you have to put some of this stuff like onto disk, but you still want to have fast horizontal reads. And that's the true challenge here. Luckily, all those more vertical queries are usually for the present and are all in RAM. Okay, I think that's the most important part about this slide. Now, how to do something that is not just in RAM. And there is a well-known approach. You can even look this up. Google published that when they did their public BigTable offer, because they wanted to tell or teach people how you can implement a time series database on top of a key value store with BigTable semantics. And that's broadly how it works, already applied with like Prometheus labels. So you have some HTTP request counter with labels. This is how it works in Prometheus. You count by status code and by get. It's all separate. And then you put the timestamp. This is your gigantic BigTable key, and your value is just your sample value. There you go. The interesting thing is, naturally, this is sorted by timestamp for each unique metric with unique label set. So this is essentially a horizontal query. It's just scanning the BigTable space. That works quite nicely. So here are my sample values. Great. Now you could use a real BigTable. Hadoop, HBase, OpenTSDB is doing this in a way. Now we wanted to be on local disk, so we used LevelDB, right? Local disk storage with key value store. That's just for the raw sample storage. You also have to do indexing, and this is one of my punchlines or Prometheus proverbs. Labels are the new hierarchies. What does that mean? So here you have a hierarchy, as you probably know from Graphite. So you can, if you go along those hierarchy, that's great, right? I have an API server service. I have an IP number where an instance runs. I have the tracks endpoint. I have GET requests with individual counters for status codes. If I now want to know, okay, how many GET requests have I served? I just add this all up. Fine, right? If I aggregate up the tree, that's fine. If I want to know how many posts do I have fleet-wide, and only the successful run start with a 2. Then you have something which is like a key which is like a full table scan in a relational database. You have to go down every branch here to find the post branch and find where the 200s. That's super expensive in Graphite. Prometheus and some others, as we have seen here, this is like the new, this is why I call it the new hierarchies, right? It's the general trend. We just have labels for everything, and every label is made equally, right? You can just query for labels. That looks like that. This is now first PromQL in the talk. So this is the Graphite dotted metric thing. I'm actually not sure if 2 star even works, but let's assume it works. So this would be the expensive query, where every star in the beginning of the dotted string means, yeah, full hierarchy scan, expensive. Prometheus, you just specify the labels you want. You can even do regex matching, and it's essentially made for that. It has indices that makes it easy to find the time series. So indices plus raw sample storage means LevelDB all over the place, right? LevelDB, key value store with BigTable semantics. So we did this in our prototype. That worked. great, right? We could reuse existing components, didn't have to reinvent the wheel, could actually focus on our awesome semantics and PromQL and how we collect metrics and instrumentation library, all those things I mentioned in the keynote, proving that Prometheus is not just a time series database. So, but that wasn't good enough. For one, as you can see here, this looks super wasteful, right? Like so much redundancy. It's not bad with LevelDB because it all runs through snappy, fast compression algorithm. Before it hits the disk, it's all compressed. But what we have in memory is super, super wasteful, right? So we had to do something about it, and especially the more you have in memory, the better you can serve. You want to serve from memory, same with all the databases. So we wanted something that is already compact in memory. So for the raw storage layer, we created a custom layer. And so we started with how can you do this? Then we wanted fixed size chunks to make the Go garbage collector happy. And we didn't want to reinvent the wheel and implement a whole lot of stuff. So we did something like every time series will result in a file on the file system. So we can use some features of the file system, or abuse, as you might argue. There's a whole talk about this, which I gave at PromCon last year in Berlin. So I won't repeat that talk. This is like going into all the details, and also a very intriguing thing. Justin is already looking at me. So we wrote this in the open, but kind of secret, because it was a GitHub org. Everybody could look at it, but only like initiated people knew about it. And then people like Justin sat at Facebook and hacked something, an in-memory time series database. And then they wrote a paper, and we kind of made our Prometheus thing more public. And you realized, oh, there are actually some similar things in it, right? And this is especially the in-memory compression. Like, we had very different premises. We wanted more data volume than in memory. We wanted to be able to query it. We were also very concerned with how to query it on the server, with the PromQL on the server and the whole engine. Well, Gorilla, or Berengay, I hope I got that right, has like, it's just in memory, not concerned with querying. It will hand out whole chunks to the client. But still, there are a few things that are similar. And it's in this talk, I like go through the original Prometheus implementation and through Gorilla, Berengay. And also later, we created a different encoding that is closer to what Gorilla does. And it's all in the talk. And it's also a trade-off. Like if you ever have used Prometheus, there's a chunk encoding flag, which essentially decides if you want to do traditional Prometheus or the Prometheus Gorilla mixed approach plus additional ideas thing, which makes your compression better, but your query is slower. So you cannot have the cake and eat it. But there's the third generation storage layer looming at the horizon. So this is happening in Prometheus 2, not yet released, pre-alpha. And this is where one of our most active developers, Fabian, he decided I will rewrite everything, essentially. So completely custom time series database with sophisticated indexing, no app using the file system anymore. That also allows us to finally use mmap, which is, we should have done this from the beginning, but we had too many files, blah, blah, blah. So there's a whole blog post about this, super interesting read. You should look at it. But I'm not talking about the storage layer now, I'm talking about PromQL. Storage layer is just important to know because that backs all the data you get with PromQL. Now, in the keynote, I already mentioned bold bat. You throw a language that nobody has seen before at an unsuspecting open source database community, and they should all learn it, right? Yeah. Worked, right? But also, we didn't just cook this up out of thin air. We all had an inspiration. And luckily, there's this blue awesome book now. And everything is now more or less well known and in the public. And you even have this nice quote, which you also have on the webpage. Even though Borgman remains internal to Google, Borgman is the monitoring system that inspired Prometheus. The idea of treating time series data as data source for generating alerts is now accessible to everyone through those open source tools like Prometheus, Riemann, Hacker, and Bosun. So, I mean, you see there's a proliferation of those tools. It's not just Prometheus. But in the book, you can actually see Jamie Wilkinson, who wrote this chapter, he also has stuff there, how Borgman really works with the query language and everything. And you can clearly see this is our inspirational spiritual grandfather or whatever. So it's not that we just thought, oh, let's just create this from nothing. However, he gives a shout out to certain open source monitoring systems. I want to give a shout out to OpenTSV. Was also mentioned here. It's way longer in the wild than Prometheus or many other systems. OpenTSV popularized this label data model, right? So they don't really have a powerful query language. They arguably have no query language at all, but different thing. But the label data model, that is what essentially, this is the first principle where everything is derived from. If you see the label time series and then you think, okay, what do I do with that? I want to aggregate along label dimensions and stuff like that. Then you realize, okay, I should actually have a query language that is dedicated for that purpose and not tries to simulate like SQL or something. And so no query language, but the data model. So this is actually, it's also a former Googler who did this. Perhaps not a coincidence. Okay, now I will compare a few queries in like SQL-ish languages and PromQL, but this is an unfair comparison. Every comparison is unfair, but one thing is a SQL-like language is always also concerned with update queries, right? So not only select, also update. PromQL is not concerned with that. It's read-only. You can see this in the architecture diagram. This is all the stuff how Prometheus pulls in data from those components of the ecosystem. This is retrieval, and you see PromQL is just the other side. It does a lot of things. You can write alerts. You can do like dashboarding. You can have like custom clients here, but it's not concerned with modifying the database. Okay, so this is probably one of the most often used queries in PromQL. So this is the metric name. It's underscore total because it's a counter. That's just a convention we have. It's a pure naming convention. It's not enforced in any way, but you should follow it. So this counts incoming HTTP request. And the rate is the thing I talked about. It's essentially the first derivative normalized to per second. So over the last 5 minutes, how much has this counter increased per second? That's the rate, right? So QPS. Great, right? If you actually execute this on your Prometheus server, you get something like this. So this is the web UI of the Prometheus server, which has an built-in, the graph tab is the built-in expression browser. So you hack in this query, and then you get gazillions of results, 62,000 actually, because that's a pretty big Prometheus server. And you see how that looks like. Like every incoming HTTP request total metric has a lot of labels, right? So this is all coming from different, in this case, really Kubernetes ports. We have a port ID somewhere here. The instance label is the port ID here. It's usually an IP number, but we put the port ID there. And you see it has a job, and then even different things, like different status codes. Oops, spoiled it. Different software versions, like it's all in the labels, and there are 62,000 combinations of labels. Usually you don't want to look at all of them. It's also a pretty abusive query. Usually you would aggregate this in some way. But just that you know, if you do this like very low-level query, that's what you get. It's a vector of things, right? It's all about vectors. Okay, now in a SQL-like query, now I've seen just in the talk before this, whatever, I saw the blur now. The Square people, right? They have this query engine based on blue something, right? Yeah, okay. So their SQL-like dialect is already pretty much optimized to that use case, but if you take like the vanilla SQL thing, the problem here is you want to have all those labels still in the result. So in a select statement, you needed to specify all those labels, but you cannot say select star because then you would get the value as well, but you want the rate of the value, right? So this is kind of, the labeling is kind of built in implicitly here, and it makes it really weird in a SQL typical query. If you aggregate it, and that's what you usually want, things look way more natural if you compare those two queries. I mean, it's still more verbose, but it's more natural. This is now a different query. I mean, IoT people always want to use Prometheus, but it's not really made for that. But still, I pretend we do we have sensors all over the world that measure temperature in Celsius, and then they are labeled by the country and by the city. But you have multiple sensors per city. And this is where you want to select only sensors in Germany, right? So this is a label selector. And then you will aggregate. You don't want to average all of Germany. You want an average per city. This is how it looks like, right? So this takes all the sensors in each city and averages them. And then you get again a vector which is labeled with the city. So and that looks that way in a SQL-like, SQL-ish, whatever. So pretty natural, right? What gets totally crazy is, and the Square people, that was quite interesting in the talk. They do a similar thing here. But this is very natural in the Prometheus world. You have some error rate or counter, and you want to divide it by the total number of requests, because that's an error ratio. You can do times 100 to get error percentage, right? For a specific job. But again, this is per instance, per whatever you have labeled. It's all a vector element matching here. You match the labels on both sides. Whenever the label set is the same, it does the division here. So in a SQL thing, this is super weird, right? You have to, again, to select all those labels you want. Then you have errors.value divided by total.value from errors where errors job is foo and total job is also foo. And then you're in some kind of complicated join statement. You have to join up all those same label sets, right? So this is all explicitly formulated in a SQL-like language, super natural in Prometheus, in PromQL. Okay, now arithmetic. That's also something you want to do a lot in metrics-based monitoring. Simplest thing, add 1, right? This will add 1 to every vector element, and now this is real stuff, like real graphite, as also has a query language, and real InfluxQL. This is also unfair comparison because Influx also has, I have to get this right now, tick script in capacitor. Exactly. It's so great to have you here. So tick script also fulfills fills a gap that also PromQL fits. So it's like overlapping concerns in a way. So it's not 100% fair. But these examples are all from a blog post by Brian Brezel. It will be linked on the last slide, so you can actually read up all the context there. It's just fun to look at it. Like very natural in PromQL, you add 1 to each vector element. In Graphite, you can do something like that with like wildcard selectors. It's probably like semantically, it's pretty much the same. It just looks a bit more clunky in InfluxQL, but still fine. If you actually have other functions, again, very organic in PromQL, almost as smooth in Graphite, and this just doesn't exist in InfluxQL for some reason, right? But Paul is working on new query language for Influx. Okay. Now, again, if you go cross-series, things get weird. Very organic in Prometheus, you want to subtract one series from another. It's not one series, it's a vector of series, right? Again, it will automatically match all the labels, and matching label sets will create the difference here, and you get a vector of differences. That happens all the time. This is even possible in Graphite, but it looks super weird. This works with, I think it's called values, but what are values in PromQL are more like measurements in InfluxQL, and there it doesn't work. So it's also a bit weird where you probably would go to tick script for. Now, where it goes totally crazy when you combine all this stuff. So this is, we can dissect this a bit. This is essentially, give me outliers. Give me outliers that are more than 2 standard deviations from the average. So again, our temperature Celsius. Now, instance would be the label where you see the instance, the individual sensor. So I'm now averaging all the temperatures, but I'm ignoring the instance. So I'm just aggregating away the instance label. So I get probably all temperatures in one city, because we have city and country labels. So I don't average the world. I average like every label combination except instance. And then I take, for the same set, I take the standard deviation, which is another aggregation operator. And then I check which individual temperature is now greater than average plus 2 times standard deviations. Now the label matching doesn't work, because here the instance label is gone, but for individual measurements we still have the instance label. So we have to tell PromQL, but don't look at the instance label, and now a value here will match multiple values here, right? Because I have multiple values from, let's say, Berlin and Germany, and I have an average for Berlin and Germany. So I have to tell it group left, so the left side has a higher cardinality. So this is the black matching of label of vector matching, which is a bit complicated, but it's all built in the language, and you can formulate things like that. And this is not possible in Graphite and not possible in InfluxQL, probably possible in TickScript. So this is something happens all the time when you build alerts. It's all at your fingertips. All right. How do you even query PromQL queries? You can use this internal expression browser, but it does nothing else here but using the HTTP API of Prometheus. So it's documented under this link. Grafana uses the same API to write, to spit out those beautiful dashboards, and you can write your own custom client. Like people always ask us for anomaly detection, business intelligence, machine learning. We don't want to build this into Prometheus, but you can use the HTTP API to get the data out of the TSDB inside of Prometheus and feed it into whatever system you have for further processing. This is how it looks like in the documentation. So this is the so-called instant query, API v1 query. You just give it the query string and a timestamp which you could leave out, then it's just now, which is most of the time what you want, right? Range query is what dashboards usually do. So you get a start and an end timestamp and a step, essentially resolution, and also query string. And this is how dashboarding works, right? You evaluate the same query at various points in time and connect the dots, and then you have your graph. Okay, now this is how it works internally. I promised live of the query, right? So you send the query via HTTP API, and then there's the so-called PromQL engine, which analyzes the whole syntax tree and does the vector matching and everything, adds it all up, and it kind of breaks this into atoms, and atoms are like for every time series that the indices tell you what has this label combination and everything for every resulting time series. Please give me the values in this time range from that time series. So what this PromQL engine talks to the storage layer with this simple interface. So there's an instant query, which just essentially gives you a single point in the time series for a certain timestamp, and the range query, which gives you a whole range. Confusingly, that's not the same as range and instant on the HTTP API, because, for example, our rate expression is an instant query. Give me my QPS now, but it has to look 5 minutes back. So this will turn into a range query over the last 5 minutes. But yeah, label matches, that's what you see here. This is what you can also use with this syntax in PromQL. That's just passed through to the storage layer. So you can say a label code, status code has to be 404, or give me all series where the status code is not 404, or give me regular expression matching or negative matching, and you can have any number of them, and they will all be, it's like it's an AND logical connection, right? So you get the label, the series where all the label matches apply. And then the storage goes to disk if there is something not in memory yet, and retrieves it from memory. And now there's this interesting thing with in-memory compression. I mentioned that, right? What Gorilla gets so great and what we also did for different reasons. But like Gorilla just keeps everything in memory. We want to keep as much as possible in memory so we don't have to hit the disk if we answer this query. Okay, indices. I wanted to explain them quickly because this is the stuff that has nothing to do with the raw storage data, but you need them, right? So we have slightly simplified and also Prometheus 1.x. So in Prometheus 2, it's all a bit different, just a bit, not completely different. So we have this one index where the key is a label name and the value is all the possible label values for that key. Like let's say label name is code, and then all possible values are 200, 404, 503, whatever HTTP status codes are in your database. The other one is a bit confusing because the key is the label pair, which is in itself a key value thing, right? So let's say code equals 404. This is the key in this index, and the value is all series that have code equals 404. By the way, the metric name in this view also becomes a label, underscore underscore name underscore underscore equals metric name, right? So the metric name looks special in the syntax, but that's essentially syntactical sugar. It's just a label as everything else. Pro tip, you can even use this in PromQL instead of the metric name. That works. Like, for example, you want regular expression matching on the metric name, you can use that syntax. Okay, so these two indices exist, and this is how it works. So usually I don't put so many words on a slide, but this is just the algorithm, right? So you get negative and regex matchers in your metric, in your label matchers. That's the complicated one, right? A code unequal 404. What does that mean? I need all codes that are possible that are not 404. So I have to match, look this up in this label name, label values index and transform this into normal matchers. And you need the union and not the intersection. So it's possibly quite expensive. And then look up possible series for each simple matcher using label per series. So for every label name, label value pair, I know which series are applicable, and then I intersect, or for those negative matches, I take the union, and I end up with a bunch of series where all those label matches match as required. So for those series, I find the chunks for the requested time, instant or range. Like instant is easy, I just have to find the chunk that contains that point in time. For range, I need possibly many chunks. Load them from disk if needed, and pin them into memory, because it would be horrible if the chunk disappeared onto disk if I'm needing it, right? So and then you get iterators. I didn't point this out. You have series iterators. Like you don't materialize the whole series. It's all just in memory in this in-memory compressed format, but it can be accessed with this series iterator. So then the PromQL engine does its thing, matches all the labels, adds everything up, divides whatever the arithmetic is, creates the result, returns it back via HTTP, and closes the iterator, which will unpin the chunks from memory. We keep them, least recently used, in a cache, to answer queries from memory if we can. And that's the life cycle of a query, right? So here you see it, big picture. So this is the GET request, right, where you have the query string here. Like this is a typical one. You have like errors per second divided by total requests per second, which gives you an error percentage. And the PromQL engine breaks this into atom. It's in the end a query range for now minus 5 minutes for a series that has this name and this job label. This is not a series, that might be many series, and the same for request total. And then the storage finds out what series these are and gets the chunks from disk if they're not already in memory, like chunks for now up to 5 minutes ago, from 5 minutes ago to now. This is the thing with those labels, like this is unique series, might be thousands, and gets them, calculates everything, returns it, and there we are. That's the life of a PromQL query. Okay, I promise credits. This is the Julius Folt's talk about Prometheus design and philosophy, where there's a lot of stuff. Also, this religious push versus pull question is all discussed there. Full recording online, and has all the examples. Why is PromQL? Why did we use a PromQL like this weird language instead of just doing something SQL-ish? And this is the blog post that compares Graphite, InfluxQL, and PromQL. Very interesting, way more examples, way more discussion. Also now, after this conference, we have to add a few more query languages, I think, to be complete. But yeah, you will get the idea. So that's it. I have also this, I think they sent the slides to everybody in the conference, but I also documented here on this GitHub repo, so you can get them here. Okay, thanks. So I do have stickers, the new edition, the shaped ones. CNCF produced, so you can get them, but you can also ask me questions. We have like 10 minutes left. You can ask me about PromQL in the talk, but if you have any other Prometheus questions, I'm now here for you. Yes, please.
I already got my sticker. But so when at query time, if you have unaligned time series and you're trying to do a group by with them, or if some chunks within the time series are missing data, how do you align and deal with those missing values?
So I think there are multiple questions. I should repeat the question, right? So and then we'll see if I get right. So first, the unalignment, like you have multiple series you want to group, have multiple series, and the chunks don't align properly, right? And then this was the first part, and the other part is what happens if there are like gaps in it, right? So now I need a whiteboard, but I'm the whiteboarding person. So the one thing is the chunks are really per series, and they are fixed by size. So we had this idea. Also, when we wrote this, garbage collection in Go was way worse than it's now. And we had this idea, constant size memory allocation is much better for the garbage collector. So always 1 kilobyte, but that's per series, so the time they span is actually super variable, right? It also depends on compression and when the time series starts. So you have this zigzagging, right, in the time series space, but that's all resolved by the storage layer. So if you have a range, it might just start in the middle of this chunk, go into the middle of the next chunk. The next time series might have a chunk in the middle, whatever. It finds that out, like we have meta information, where does each chunk start and end. In Gorilla, for example, the chunks are just fixed time and not fixed size, which simplifies things, but they also didn't use Go to implement that. And in the storage v3, in Prometheus 2, which is also quite confusing, this will all be different, and we essentially have time blocks, and the chunk size is not constant anymore, like it's all very different, but then you have kind of implicit alignment. Talking about gaps, this is just natural. Like it's natural that a time series stops, it's all dealt with in the storage layer. It's, yeah.
What about query time though? Let's say you expect values every minute, but you don't have the timestamps aligned depending on the collection.
Okay, now I get it. So question is, timestamps are not aligned, what do I do then? This is actually a very good question, just a different direction than what I initially thought. People always think about the Whisper format from Graphite, right, where the alignment is baked in, right? So you pre-create the file, and it's like every minute you have this sample, and it's carved into stone, into magnetic tape, disk, whatever. So in Prometheus, while we try to have regular scrape intervals, that's what the Prometheus server does, and that's also what makes the compression so awesome, that you essentially don't have to have like a millisecond precision timestamp every time, but you just know, yeah, it's just another 10 seconds passed since the last timestamp. That's good, and that's usually happening, but we don't depend on it. Like we have a millisecond precision timestamp on every data point, compressed, of course, as far as possible, but it's there. So if you have like a tiny blip in the network, or the Prometheus server had a hiccup, garbage collection pause, and it's like 10 milliseconds later, it will all be recorded in the timestamp. If you miss a whole scrape, then you have a scrape missing, and the next timestamp will be surprisingly large, but it's all there. And if I do like an instant query, I just go back until I hit a sample. And with the count implementation, if that's more than 5 minutes away, we'll say, no, there's no data. But if it's like 4 minutes and 59 seconds away, we'll say, there's data. It's just a bit old, but it's still there. That's essentially how it works. So it's Prometheus also made to tolerate missed scrapes, essentially. So we have 10 more minutes. Great, and we're already in the question section. Okay, more questions?
Can you talk in general terms about the deployment of Prometheus at SoundCloud, like what kind of machines it's on?
So we have we don't run Prometheus on Kubernetes yet, which is like the nicest thing, because they are kind of, a colleague of mine said they are like twins separated at birth. Because you have this weird line of inspiration where like Kubernetes was inspired from Borg. Now but we don't need that anymore, right? It's there. And Prometheus was inspired by Borg-Mon, which like the name is very similar, but it's essentially very different things, right? But you have this family tree in a way, and now they kind of are reunited in the CNCF and play so nicely with each other, and Prometheus is so nicely suited to monitor stuff on Kubernetes and Kubernetes itself and all those things. Now you would run Prometheus on Kubernetes, but Prometheus, because it has this local storage, it's a stateful app, essentially. I mean, you could say, okay, I don't care if I get rescheduled, I start with an empty data storage, but usually you do care, right? So this is why it's harder. It's like essentially the same as running MySQL on Kubernetes. So at SoundCloud, at the moment, we are very much focused on getting all our stateless microservices on Kubernetes. So we run all the stateful stuff, Chef deployed on either bare metal machine or EC2 instances, which means, every team gets their own Prometheus server because it's pretty easy to handle. Like we don't have this approach where we have like gigantic central servers, and they spin it up on EC2 if it's small, in our data center on a bare metal machine if it's bigger, and that works quite nicely. But yeah, different things are possible, like CoreOS operator was mentioned in the previous talk for TSDB, right? So there's a CoreOS operator for Prometheus. So if you want to run it on Kubernetes and you want like easy click a button deployment, look at the CoreOS operator for that. So it's all kind of possible, and various people do different strategies there. All right? Okay, somebody else was like twitching. Yes, please.
Non-technical question. I'm working curious about the organization that's kind of behind Prometheus. You mentioned there was a foundation.
Yeah, the CNCF, Cloud Native Computing Foundation, in case you don't know that, that's a sub-foundation, I don't know if that's the real word, of the Linux Foundation, which was essentially built like kind of a specialized subgroup for cloud native technologies. So that was essentially, I guess, bootstrapped with Kubernetes as their first project they host, but they also organize conferences and stuff like that. And they make stickers, like shaped stickers. It's like you need a foundation for that. And Prometheus was the second project, but now they have like a whole like 9, also like Linkerd and I mean, a number of projects are in there now. Open tracing, loads of interesting stuff. And that's essentially, so Prometheus doesn't have a company behind it, right? I mean, it was initially developed mostly at SoundCloud, but it was never meant as the SoundCloud thing, which SoundCloud now, like whatever, generously donates and supports and whatever. We do music streaming, right? We don't do monitoring. It's like to connect to Paul's talk. There is no business behind Prometheus in a way, right? It's just we needed it. It really didn't only simplify things. We just, at the time when we started it, there was nothing that could have done what we are doing now with Prometheus, right, in the open source space. And other companies felt the same. And like there are like vendors like CoreOS or Weaveworks that kind of offer that to their customers, but the project itself is still something that is like not like primarily connected to any company. So this is when you think, okay, but who owns the domain and whatever, should we ever have a trademark? Like should that be some random person in the project? Then you think, okay, we want some foundation that hosts us essentially. And so far that works quite well. I mean, there is a graduation in the CNCF, which no project has yet accomplished after half a year or so. So hopefully later this year we will graduate, perhaps even before Kubernetes, and then we are the first proper project in the CNCF. Okay, and I didn't repeat the question, but I think it was obvious what it was for. Do we have, I think we have a few more minutes. Okay, great.
You actually mentioned OpenTSDB as the initiator that had a label approach to time series, and that was also an important one. Why does Prometheus actually added double quotes around the value of the label?
Okay, question is with all the label model, so like established before prior art by OpenTSDB, why do we add double quotes? This was before I joined the project. I think we really wanted UTF-8 strings, which like you might have Chinese label values or my own name with an umlaut, or so that all works. And like the font, like OpenTSB is very restrictive with label values, which is, by the way, you have this remote write and read adapters now. Is it called adapters? I got that wrong once. They renamed it. I think it's adapters now. It might be the wrong thing. Where you can write Prometheus data into some external distributed storage backend for eternal storage, essentially. And if you use OpenTSB and you have like Chinese in your label values, it doesn't work. Or like things that are operators in OpenTSB, whatever. OpenTSB is very restrictive with the label value, and I personally don't like that, but we have the same restrictions on like metric names and label names, right? But I mean, in certain cases it was quite helpful that you could just put emojis into your label value. Like,
need the codes for that. Because you're parsing it internally from Prometheus anyway.
Yeah, you could. And then the comma and the curly brace, and then what do you do with your curly brace in your label? Yeah, it's...
URL encode that.
Sure, yeah. Totally agree in principle. I think it was really just, this is like an opaque string, let's put it into double quotes. But it wasn't even my decision, right? So I can't look into like Julius's or Matt's head, but I could ask them what was their original incentive. But yeah, it's kind of peace of mind, but you still have to escape double quotes then, right? So it doesn't really help you in that way, but we had weird things in. Like we had this relabel expression that would all 503s would be replaced by pile of poo emoji. That was quite helpful. Okay, anything else? Yes, please.
On the subject of long-term storage, can you talk a little more about that? I mean, what we're doing right now is we have the second Prometheus service straight from the first one every 5 minutes and storing that for like a year.
Yeah. With federation.
Yeah, federation.
Yeah, okay. Yeah, that's a valid workaround in my case, in my opinion.
So that's like the recommended way to do that. I know there's like the plugins that you mentioned as well for long-term storage.
So question is recommended way for long-term storage, and what you're doing is federation. Like you can, federation is an idea where a Prometheus server scrapes metrics that are already in a different Prometheus server, right? That's very nice. The original intention is not for long-term storage, but like global scalability. So you have a local, let's say, per data center Prometheus server. You pre-aggregate certain metrics, and then you have the high level already aggregated on the data center level metric, and you federate this into a global Prometheus server that then gives you like the high level view. What is my average latency globally or something like that, average QPS. But you can use this, of course, to have the master federating server scraping less often and also only selected metrics. And then you can certainly, with a 1 terabyte disk, have probably 10 years of retention, and it's no problem. So this is kind of a poor man's perpetual storage or something. So yes, you can do that, but these adapters for remote write and remote read are kind of recommended, but they are thank you, but they are very experimental. So the exchange format might still change, and it's all it still needs to be battle proven and everything. So. But that would certainly be the way to go. Also, Weaveworks already has a solution which is kind of related. They tried that early for their customers, so they offer for their customers Prometheus data collection with long-term retention and durability and everything. And they wrote like a distributed storage bank. It's called Cortex. It's also open source, but that's related. Like all those efforts try to align. And get you something in the end where we can say, this is the way to go. Put everything into whatever InfluxDB or something. Like, there are so many interesting conversations at this conference. All right, now we have 30 seconds left, so I think we have to conclude here. There are still stickers if you want. And thank you for being here.